All right, this is the video lecture for Pre-Calculus Unit 3, Lesson 1. Again, I want to point out here that for this one unit here, we are going to go ahead of where we are at in Algebra 2. So we're going to work on polynomials and rational functions, even though that is the next unit in Algebra 2. So we'll cover some of this, and then we will, when we go back to Algebra 2, we will highlight and go a little bit more in depth into some of those features. All right, but for this, we're working with polynomial and rational functions. So if we're looking at the overview for Unit 3 here, just real quickly, all right, you should have some practice with writing and graphing functions, all right? We've done a lot with linear and quadratics up to this point, but what happens when you come across an exponent that's larger than 2, right? So if we get something that's higher than just x squared, the question becomes what happens, right? And so that's what this unit's going to deal with. All right, and the question might be is where might this be useful, right? And a lot of these scenarios are used in like businesses, right? Right, so economics, a lot used in geometry, right? Figuring out how to design the most optimal shaped water bottle or container, right? Things of that nature. And these scenarios belong to this class of function known as polynomial functions. And we've talked about it a little bit here in general, but now we're really going to focus on what this means and how do we use it. So moving forward here with Unit 3.1, we're talking about polynomial expressions, right? Polynomial expressions. So we've done a lot of work again with linear and quadratics, and that's helped us build this kind of foundation for exploring these things called polynomials. And so a lot of polynomials, though, however, will have more complex things than just our x to the first power x squared, right? So more than just that linear or that quadratic function. But we're going to cover more foundation stuff and how this is going to be used moving forward in different mathematics. And we'll even look at some things that are going to be used in calculus called limits, right? But we're gonna keep rolling here. So for polynomial expressions here, okay, so the question is what is a polynomial? All right, and to begin to look at polynomials, the smallest form is known as a monomial, okay? Monomial. It's an expression that is a real number, a variable, or a product of real number and variables that have whole number exponents. And let me highlight here, whole number exponents means they are non-negatives, right? They are non-negatives and they are whole numbers, right? They're integers. So 1, 2, 3, 4, 5, 7, 12, 100, right? So expressions that are monomals, x to the third, t to the third, right? Y fifth, even negative 4mn to the 7th, p to the 11th, right? All of those because those exponents there are positive and they are whole numbers. Something that is not a whole number would be this square root here. Technically, this square root stands for x to the 1/2, x to the 1/2 power. And if you don't believe me here, look over at my calculator. So if I do 16 to the power of, let's go with 0.5. Oh, sorry about that. Let me clear this out here. So 16 to the power of 0.5. That's 4. Same thing as if I would have done square root of 16, right? So when you see a square root, that's saying something to the power of 1/2, right? So 3/2 again is not an integer. It's not a whole number integer. Okay, so what that one is saying is I'm going to take it to the power of 3 and then I'm going to square root it. So what that would look like is if I had something like this, right, and then I wanted to put in x, oh, sorry, that's a d value there, so let's put in d to the power of 3. To the power of 3. So that's really what that's saying, is we're saying d to the 3/2. Well, I'm going to cube it and then I'm going to take the square root of it, right? So that's what that one's saying. Okay, now if we have things that are to the negative power, right? So y to the negative 1/3. What that's actually saying is it's saying a fraction, right? So it's saying a fraction of actually 1 over y to the power of 3. Okay, so again, that is not a whole number, and that is not an integer. Okay, Same thing here. We've got 6g to the 10th. So technically everything up here is totally fine, right? We've got 5e to the power of 2, right? We've got f to the power of 9. But then here we've got 6g to the power of 10, right? So even if I were to go back here and go 5/6, so let's go there. Let's get rid of that 6 on the bottom. If I go 5/6, right? I've still got that g to the 10th on the bottom. So really what that's saying is g to the power of -10, right? And that's really what that's saying. So since that's a -10 there, that's not a positive integer. So unfortunately, that one is not a monomial. All right. So if we go through this here, I've got x squared. Oh, sorry. I've got, there we go. Okay. I've got x squared to multiplied by y. So again, what that one is looking like here, just for full calculator sanity here. All right, so we've got 1/3 multiplied by x to the power of 2 multiplied by y. All right. So that's what that one's looking like. But the way that they typed it in is how you might type it in on your calculators. But that's what that one stands for. All right. Now, this one here has 3 different terms. It has that x squared, the x, and then the constant. So that's not a monomial. That's got 3 different things. All right. SQRT, that means square root, right? So square root is not a monomial. Same thing here. I've got multiple terms, not a monomial. Multiple terms, not a monomial. I've got 1/x, which is like saying x to the -1 power, not a monomial. All right. This one here is just r times s squared. So that one looks like rs to the power of 2, right? So that one's totally fine. Okay. 13 is a monomial, right? It has an x to the 0 power. All right. This next one here is not a monomial. Okay, it's not a monomial. It's got multiple terms here. If I actually do my FOIL, right, we get that x squared plus x plus constant, right? So that's not a monomial. But this last one here, -2x, that's x to the 1st power, so that is a monomial. All right. Moving forward here. Each monomial has a value called its degree, right? And the degree is if we add up all of the exponents of the variables. So 2/3 x to the 3rd, y to the 5th. So that's 3 plus 5. That gives us a degree of 8. Okay, same thing. rs squared here. We've got a 1 for the r, right? That's technically r to the 1st power plus s to the 2nd. So 1 plus 2 is 3. Even if we look here, we have m to the 1st plus n to the 7th plus p to the 11th. So 1 plus 7 plus 11. That gives us 11, right? So again, making sure we understand what this means terminology wise. This is saying x to the power of 2 times by, I gotta bring that down, times by y times by z to the power of 3. That's what that's saying. So I've got 2 plus 1 plus 3. That gives me a degree of 6. All right, same thing here. I've got 2m times n to the 13th. So 13 plus 1 gives me 14. And then -z, okay? So just because you don't see it, it's still a 1 though, okay? So it's z to the 1st. All right. So then moving forward here, okay, you've seen what a monomial expression is on that last couple of slides, right? And if we put several of those together, we create these things called polynomials, right? And we've done a lot with polynomials, and it's basically adding or subtracting monomals together, all right? And again, we've done a lot of this with our linears and our quadratic equations, all right? So here's a couple examples of just monomals getting added together to make this polynomial expression, right? And in general, there's the general form for a polynomial, right? So we start with something to the power of n, right? And technically then you have something smaller every time. So n to the, let's say with 5th plus some value, n to the 4th plus some value, n to the 3rd plus, all the way till we get down to just a constant by itself, right? And a to the nth, that first one there, that first term there cannot equal 0, right? We have to have some value there. So if it a to the nth is equal to 0, then that's not the first term. You got to back it up 1, right? So again, you've got to make sure you have a constant, a term, a constant and a variable to some power, right? To give us a monomial here. All right. Again, the exponents are whole numbers, coefficients are real numbers. So if we watch this video together here, it'll give us a little bit more terminology.
To illustrate the important terminology associated with polynomials, it will be helpful to take a look at a specific polynomial function. Polynomial functions are formed by adding or subtracting monomial expressions. These are called the terms of the polynomial. When you write a polynomial in its standard form, you write the terms in order. So the largest exponent is written first. The largest exponent is also called the degree of the function. The degree of a polynomial is important in figuring out how its graph will behave. The coefficient of this term is called the leading coefficient. You'll notice this function looks a lot like the quadratic function you are already familiar with. That's because the quadratic functions are polynomial functions. In fact, this term is called the quadratic term because of its exponent. Similarly, this term is the linear term, and this is called the cubic term. The term at the end that has no variable is called the constant term.
All right. So again, this should look very familiar here. And if we can follow patterns, we've got quadratic, we've got cubic, you can probably guess what's going to be next here. All right. So when we're naming polynomials, okay, we've got two basic criteria that they get classified in, okay? Number of terms and degree, okay? So the number of terms and degree. So when we need number of terms, we mean, okay, there's one term here, there's 1, 2 terms there, 1, 2, 3, 1, 2, 3, 4, 5, right? So if you've got one term, you're a monomial, 2, you are a binomial, for 3, you're a trinomial, and 4 or more, you are a polynomial. Okay, so 4 or more gives you that polynomial name, right? And you can notice here, it doesn't even matter for these what exponents they've got, okay? As long as they're that whole number and they're positive, doesn't matter what exponent they have, right? But when the exponents come in play here is under these degrees, right? So if we've got a x to the 0th degree, it's like saying x to the 0th, right? And that would give us a value of 1. So technically, 5 times x to the 0th is 5. Okay, so this is just the constant. If you have a first degree, right, that's a linear, right? That looks like our linear equation, our y equals ax plus b. All right, if we have a second degree, that means x squared. We have a quadratic, okay? If we have something, a variable to the third power, so x3, that's cubic. x4th, that's quartic. x5, that's quintic. And anything more than that would be an nth degree polynomial. So this is a 7. So this example here would be a 7th degree polynomial. All right. So when we're evaluating polynomials, all right, we're just talking about plugging in and solving for the expression. So if we've got this expression here, okay, if we're evaluating for f of 2, means x equals 2. You plug in that 2 everywhere you see x and you solve, right? And you're going to get this constant value of 24. All right, so what this tells us is where x equals 2, y equals 24, and it's going to lie on that graph of f of x, right? So if I plotted this in my calculator, f of x would give me a graph. If I plugged in x equals 2, it would bring me to y equals 24. All right, so now if we were to do this one, consider the following polynomial. I'm going to plug this into my calculator here so that we can walk through it together, how you should type this in. So I've got 2 parentheses, okay, x to the third power. So that would be -3, all right, -3 to the power of 3, all right, plus 4 parentheses, -3 to the power of 2. Okay, and then I've got minus a -3 plus 6. Okay, when I evaluate that out, I get -9. All right, I get -9. If I look at my answers here, there you go. X equals, or y equals -9. Okay, so same thing, you just plug it in, and again, being really, really careful with your parentheses. So exactly how you see it there is exactly how I typed it into my calculator. All right, so moving forward here, if that is confusing to you and it's kind of freaking you out, there is technically a shortcut, okay? And it might not seem as short at first, okay? But there's this process called synthetic substitution, all right? And we're going to look at it for the equations we just did on the last page. But let's go through this video here so that it can explain to you what synthetic substitution is.
If you think multiplying out all those exponents is tedious, then the system of synthetic substitution is for you. Start by writing the polynomial in standard form. For this equation, what is f of 2? The first thing you need to do is insert 0 terms for any missing powers, like this. Now, write out the coefficients of the polynomial. In the top left corner, put the value that you're evaluating the function with. In this case, 2. Your final answer, f of 2, will end up in the lower right box. Rewrite the leading coefficient of the polynomial in the bottom row. To fill in the next column, multiply the top left value with the value in the bottom row. Then add the numbers in the column, writing the answer below. Repeat the same process to start the next column. Multiply the top left value with the next value in the bottom row, and write the answer in the next column. Again, add the numbers in the column, writing the answer below. Continue this process to fill out the rest of the table. The last cell is the one that contains the answer, 24. This is the same answer you would get if you evaluated the function f with the value x equals 2. So, synthetic substitution is able to give you the same answer without having to multiply out all the higher order exponents in the polynomial.
Right? And again, one of the things I want to point out here is that you had to add that 0x cubed term, right? You have to add in any of the missing, right? So we would start with 4. You got to make sure you have a 3, a 2, a 1, and a 0. And if you don't, then you just add it in as you see here. All right? So on this page here, we're going to work through what one of these would look like here, okay? And I'm going to work through it for you, and then you guys can try this on your own if you want. But it says evaluate f of -3. So you plug -3 there, right? And we've got 3, 2, 1, 0, so we don't have to add any extra terms. So I write 2, I've got a 4, I've got -1, and then I've got 6, right? So we're going to continue. So I carry that 2 down. All right, then I do -2 times 3. That gives me -6. 4 plus -6 is -2, right? Then -2 times -3 is +6. 6 minus 1, or 6 plus -1 gives me 5, right? 5 times -3 gives me -15. And then 6 plus -15 gives us -9. Right? And that was our answer that we came up with originally, was that -9. So you can see it works. And again, it may seem pretty tedious right now, but again, it's picking and choosing your battles. Which do you feel more comfortable with? All right. So moving forward here, imagining the graph. Okay. So we're going to try to talk about some key similarities here, and some patterns that we can pick up here with features of a polynomial graph. All right. So if we do this here, okay, first off, we're going to notice some features about the graph. So first off, 2x minus 3, all right? So first off, we notice that the degree is 1, our leading coefficient is 2, right? Check, check. The right side of the behavior, that's there, is pointing up, while the left side of the behavior is pointing down. And there are no turns because there doesn't change direction. So there's no turns in that graph, right? Oh, sorry. I don't know why I put a 1 there. I just said no turns and I typed in a 1, right? So no turns in the graph, all right? Now, if we look at this one here, our degree is still 1, but now our leading coefficient is negative. So the right side of the graph is pointing down, and the left side is pointing up, all right? And again, there are still 0 terms in that graph. Okay, now what we should notice is we've got 2x squared plus 3x minus 1. So the degree is now stepped up to 2. The leading coefficient is still positive, so it's a +2 there. The right side of the graph is pointing up, and so is the left side. All right, and there is 1 turn because it goes from going down, turns, and goes up. All right, so correct, 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 boom. All right, now what you're going to notice here is I've got a degree of 2 still, but now my leading coefficient is -1. All right. Right side's pointing down and the left side's pointing down, and I still have 1 turn. Okay. Hopefully we're picking up some patterns here. Now, this is x cubed, so this is a 3rd degree. My leading coefficient is a +1, so my right side of my graph is pointing upwards. My left side of my graph is pointing downwards. And I have 1, 2 turns. So 3, 1, 2, awesome. All right, now I have a negative x cubed. So my degree is 3. My leading coefficient is a -1. My right side of my graph is pointing down. My left side is pointing up, and I still have 2 turns in my graph. All right. Negative x to the 4th. So my degree is to the 4th. My leading coefficient is a -1 there. Now, my right side of my graph is pointing down. My left side of my graph is pointing down, and I have 1, 2, 3 turns. All right. X to the 5th here, x to the 5th. So I've got 5. My leading coefficient is a +1. My right side of my behavior is pointing up. Left side's pointing down. And my number of terms, 1, 2, 3, 4. So 5, 1, 4, check. All right, now, based on what we've been practicing, you should be able to hopefully get a couple of these correct here. Okay, so our power or our degree is to the 5th power. Our leading coefficient is a -1. All right, now, based on what we know, this is a negative value, so it seems like every time we've had a negative value, the right side behavior is pointing down, pointing down. Now, the left side of the behavior is not as obvious, so let me help you out this one. This one's going to be pointing up. It's going to be pointing up, and the number of turns it's going to have is 4, right? 1, 2, 3, 4. And you might ask, how did I know that? We'll go over some tricks here at the end. All right, this one, x to the 6th. So it's 6th degree. It's a -5 coefficient. So since it's a -5, my right side of my behavior is going to be pointing down. And my left side of the behavior, again, this one's a little bit more difficult, is also going to be pointing down. Now, this one here, I didn't even put in the number of turns. But if we were following a pattern here, we would have put in 5. We would have normally put in 5. Okay, but right here it says the graph actually has 3 turns. From the equation, you can only know the maximum number of turns this graph might have, right? So that's part of the hints here. Okay, you can have a maximum of 5 turns, but without seeing the rest of the graph, you may not actually know what it has. So for example, this right here just looks like it has 3 turns. All right, so here's where the patterns come into play here. Here's where the patterns come into play. So the relationship between the degree of the function and the maximum number of turns in the graph. Okay, so the maximum number of turns was based on the number of degrees minus 1, right? So when we had a 6th degree, we could have a potential of 5 turns. Or when we had an x squared, right, to the 2nd power, we could have a maximum of 1 turn. Okay, now if the leading coefficient is positive, right, if the leading coefficient was positive, the right side of the graph, hopefully we picked that one up, pointed up. All right, and if the leading coefficient was negative, the right side pointed down. All right, and when the right and left sides of the graph have the same behavior, right, so going up and up, that was when they were even. When they were even, right, so if they were even, the right side went up, so did the left side, right? So x to the 4th, okay? Right side went up, so did the left side, which means that if they had opposite behaviors, they were odd numbers, right? So 1, 3, 5, 7, they had odd behavior because one side went up and one side went down. All right, so with the graph behaviors, okay, there was a couple of things we focused on here. All right, obviously, yes, we needed to know the degree of the polynomial and that leading coefficient, but what that helped us figure out was this thing called relative extrema and end behavior, right? And if we start off with end behavior, it's what happens at each end of the graph, right? So the left side of the graph and the right side of the graph, right? And how we can write that here is as x goes to infinity, right, with the right. So again, if we were looking at a graph, if we are looking at a graph here, okay, this is our infinity. Okay, and this would be negative infinity in terms of our x values, right? 1, 2, 5, 7,000, 5,000, right? It's going to go on forever and ever and ever until we tell it to stop. Same thing here, except now that you're going in the negative direction, so that becomes our negative infinity. All right. And same thing with polynomial functions, right and left-hand side either approaches positive infinity here, right? So this is infinity in the y direction, and this is infinity in the negative direction. Okay, so again, we were saying our right side of the behavior like this, right? So our right side of the graph might be going towards positive infinity here, right? So as we said, our right side meaning positive x value, our graph was going up towards positive infinity. All right. Moving forward here, relative extremas are turns in the graph, okay? They're like vertex points, except for that there can be multiple, right? And technically, our vertex here is a relative extrema, okay? Or a relative extreme, okay? But there can be multiple, not just one, all right? Especially for those with larger polynomials, values, okay, if it has multiple terms, it's going to have multiple relative extrema. All right. And like we said, the most extrema it can have, right, the most turns in the graph it can have is the number, is the degree number minus 1, which we show as n minus 1. All right. And then it's important to remember that it will have fewer than, it can have fewer than n minus 1, right? So that one graph where it was supposed to have 5, it ended up only having 3. So it can have up to n minus 1, but it cannot have the same number or more than. All right. So let's take a second here and review what we know now about n behaviors of our graphs.
Take a moment to review what you've learned in this lesson. For a polynomial function with degree n, its graph will have at most n minus 1 turns. In other words, the graph of a polynomial can have as many maximum or minimum values as the highest exponent minus 1. The leading coefficient in a polynomial function determines the n behavior of the graph on the right side. If the leading coefficient of a polynomial function is positive, the graph will point up on the right side. If the leading coefficient of a polynomial function is negative, the graph will point down on the right side. The degree, n, of a polynomial function determines the n behavior of the graph on the left side. If n is even, the left side of the graph will match the right side's n behavior. If n is odd, the left side of the graph will behave opposite to the right side's n behavior.
All right. So again, those are some really, really helpful tricks and tips there. Okay, so moving forward here, we're going to go over the study guide quickly. I know this one's running a little bit longer, so I'll try to speed it up here with the study guide. So highlighting the answers here, a monomial is an expression that is a real number, a variable, or a product of real numbers and variables having whole number exponents, right? 1, 2, 5, 7, whole positive numbers. All right, so give an example of an expression that is a monomial, right? Plenty of examples that were in the apex, but one example is 9x to the 8th power. Okay, an expression that is not a monomial is something where you have a fraction or a negative exponent. All right. Now, the degree of any monomial is calculated by adding the exponents of its variables, right? So right here, if I've got x squared, y to the first, z to the third, you've got 2 plus 1 plus 3, which gives you 6. All right. So for this one, give an example of a monomial with a degree of 4. You could have just said x to the 4th, right? Or you can say something like a squared, b squared, right? 2 plus 2, anything that gives you, when you add all the exponents together, gives you 4. All right. Now, a polynomial function is defined as a function in the form of right here. We've got an x to the nth plus n minus 1, x to the n minus 1, right? An example of this is where n might be 4. So you have some constant, right? So some coefficient there times by x to the fourth. Then you would have some coefficient times x to the third, some coefficient times x to the second, times x to the first, times by x to the 0th, right? And again, where a is not equal to 0, okay? A to the nth is not equal to 0. All right, now a to the n minus 1 can equal 0, right? And we had an example of that, but when we were writing the full thing out, in order to do that shortcut way, we still had to write in x to the, we had to write in 0x to the third power. All right, again, exponents are whole numbers and the coefficients are real numbers, so no imaginary or complex numbers. All right, give an example of a polynomial expression, right? You can come up with plenty of these, but like we said, we've got a to the fourth, a to the third, a to the second, a, and then technically this is a to the 0th. All right, now for the polynomial function, p of x equals 6x cubed plus 9x squared minus 2x minus 26. The degree is 3, right? Because it's the highest degree there. All right. The leading coefficient is a 6, all right? The quadratic term, that quadratic term right there is that x squared term, so it's that entire term, so it's 9x squared. The linear term is that negative 2x, right? So that x to the first. The cubic term is that term to the third power, so 6x cubed, and then the constant term is that final one, that minus 26, right? That's just picking up on words and phrases and terms, okay? So there's an example of a polynomial with a degree of 5, okay? It's just got to have something x to the 5th, right? X to the 5th, and then you fill in for the rest of them there. Now, here's again how I knew how to figure out those answers above, right? So if you've got one term, you're a monomial, 2 terms, binomial, 3 try, 4 or more, you're a polynomial. Okay, plenty of examples there. Now, if you are degree 0, you're the constant. The first degree is a linear term, second degree is quadratic, third is cubic, fourth is quartic, fifth is quintic, and n is greater than or equal to it's just greater than 5. That's the nth degree polynomial. So again, example, x to the 9th, that would be the 9th degree polynomial. All right, so then for this one here, okay, for this one, you can do the entire thing where you just plug in for x. So for example here, if we're solving for x to the, g of x, where x is -1, okay, you're just plugging in a -1 where you see for all of this. All right, and again, being really, really careful with parentheses, especially dealing with negative values. All right, but we can do something known as synthetic substitution in order to kind of bypass all this complicated squaring and exponents and all of that stuff. All right, but something you have to highlight here is that the polynomial needs to be written in that standard form. So what that means is you can't skip any terms, right? So if we go down here, you've got x to the fourth, x to the second, x to the first, x to the 0th. You're clearly missing that x to the third term. So when you write it in this standard form, you have to add a plus 0x cubed, right? Because technically 0 times x cubed is always going to equal 0, so it's like it doesn't exist. But in order to do this synthetic substitution, you have to have all parts to it. It has to be in that standard form. All right, so again, what that would look like here, you carry that first 4 down, and then you multiply what your x is being filled in for. So f of -2 goes there. You go -2 times 4 gives you -8. Then you add those two. So -7, then times by 2, 14. Add them together. And this term here in the bottom right-hand corner is the answer for if you evaluated f of -2 for this entire function. All right. Almost done here. The graph of the polynomial function here is shown below. So if we're looking here, the degree is 4th because it's x to the 4th power. The leading coefficient is that -2. The right side of the behavior, so that's talking about over here in the positive x region, that is down. It points downward. And the left side also points downward. And the number of turns is how many times it changes direction. So 1, 2, 3 turns. All right. If a polynomial has a degree of n, its graph will have at most n minus 1, n minus 1. If the leading coefficient is positive, the graph will point up on the right side. Okay, if that's negative, it's going to point down on the right side. And if n is even, the left side will match the right side. And if n is odd, they will be opposites of each other. All right, so again, all these answers will get posted on Google Classroom here. But let's continue moving forward, and we will do the checkup here. All right, we will do the checkup, and there is only one quiz, so yes, you do have to do this quiz for unit 3.1 here. All right, but let's get started with the checkup. All right, so with the first couple of questions here, it's saying state the degree of each polynomial. So it's important to notice the difference between each of these questions. So in this first question here, we are dealing with a monomial, right? We've got one term. So when we're looking at a one term here, we actually add them all together. So I've got 3 plus 2 plus 1. So that gives me 6, right? So I've got a degree of 6. When I am looking at something like this, I've got one term here, and one term here, right? And so in order to figure out the degree of each polynomial, I have to figure out what the highest degree out of all of those terms is, right? So in this first one here, I have 2 plus 3, so 2 plus 3, right? So the degree for this term is 5, right? Now this one, it's like a to the first plus b to the fourth plus c to the fifth, right? So that is a 10th degree polynomial, or sorry, that's a 10th degree term right there. And then this is like saying any variable to the first, right? So that's a 0th power. All right, so since again, all of these are added together, I have to figure out what's the degree of the polynomial. So you choose the highest degree. So this is a 10th degree polynomial. Even though this one's 5, this one's 10, and that one's 0, you pick the highest term. All right, so same thing here. I've got a 2 for that term, I've got a 1 for that term, and I've got a 3 for that term. So overall, this entire thing is a 3rd degree polynomial. Right, and I guess I can fix that one for you too. 6th degree polynomial. So again, that's the difference between looking at a monomial and multiple monomials added together, right? You look at the highest degree monomial in each polynomial expression. All right, now 4 through 7, determine whether it is a polynomial or not. All right, determine if it is a polynomial or not, right? And so again, what we are looking for is exponents that are positive and whole numbers. All right, positive and whole numbers. And this one, okay, so 4 is not a polynomial. And the reason that is because cube root of x is like saying x to the 1/2, right? So that's not a positive and not a whole number. So this one is not a polynomial. All right, this one here, we've got 5 to the 5th, to the 4th, to the 3rd, 2nd, 1st, 0th, right? So yes, this is a 5th degree polynomial. All right, now, number 6 here, don't let it confuse you, okay? That's x squared times by the square root of 3, all right? But this is still a degree to the 2nd, plus x to the 1st plus x to the 0th. So yes, this is a polynomial, and it is a quadratic or quadric. Okay, quadratic, because it's x to the 2nd. All right, and then finally here, okay, we've got this term here, and that's 2 to the xth power. That is not a polynomial. 2 to the xth power is not a polynomial because that exponent is equal to x. That's not a whole number or positive value there. All right, 8 through 10, write the polynomial in standard form. So we'll do a couple of these here. All right, so in standard form, this first one would look like 11x cubed, right? So we go x to the 2nd plus 6x squared plus 6x squared plus 2x, right? We had to go 3, 2, 1, right? 3, 2, 1. The leading coefficient there then becomes 11, then becomes 11. And our constant term is like saying plus 0. So our constant term is a 0. All right. If we go to number 10 here, all right. If we go to number 10, our standard form for number 10, we are looking at the exponent, okay? So our standard form is x to the 4th y plus x squared y squared plus 7. All right, our leading coefficient is 1 and our constant term is 7. All right, and if you look at it too, I've got x plus 4 and a y to the 1st. So this is a 5th degree, where this one is a 4th degree, right? So you got to put it in the highest degree first, right? So that's why that one goes x to the 4th y, then plus x squared y squared plus 7. All right. For 11 and 12, state the maximum number of turns in the graph. All right. So first off, you check this is in standard form, okay? And our formula for this is we go n equals the degrees. So the maximum number of turns, so max number of turns is equal to n minus 1. So in this example here, we have n equals 5. So the maximum number of turns max is equal to 5 minus 1, which equals 4. All right. Down here, we've got x to the 3rd, x squared, x first, right? So we're in standard form. So n equals 3. Our max number of turns is equal to 3 minus 1, which is equal to 2. Okay. And then here, oh, sorry, got cut off there. All right, here might be a little bit confusing. This might be the first time you've seen it in this form here. All right, so what this is saying is exactly what we were doing in that graph. So that right end behavior, left end behavior, right? So again, if it's talking about the right hand behavior, it's talking about over here. It's talking about the left, it's talking over there. All right, if I'm going downwards, so down is equal to negative infinity. All right, and up is equal to positive infinity. All right, so what we do is we focus on knowing the degree and focus on knowing the leading coefficient, right? And so what we said was, if the leading coefficient is positive, right, then our right behavior is up. Or as we found out, it's now known as infinity, right? And then based on if it's odd or even, okay, even's going to be the same behavior on the left, and odd is going to be opposite behavior, right? And we'll work through a couple examples of what that looks like. So if we skip number 13 there because it's a little bit cut off, we look at 14 here. All right, so 14 first has a leading coefficient of 1, and it's a 4th degree polynomial. All right, so the right end behavior, since it starts with a positive 1, f of x is going to go up, which is another way of saying goes towards infinity, right? It goes towards infinity, up and up and up. Okay, and now we noticed that it is an even exponent. So it's going to have the same behavior in the left-hand side, right? It's going to be also positive. All right, now for 15 here, our exponent is 2, right? So we have an even exponent, but we have a negative coefficient. All right, so a negative coefficient means our right-hand side is going to go down. So that's going to be negative infinity. And since we have an even exponent, it's going to do the same on the left-hand side. So it's going to be a negative infinity there. All right. Now, if we look at 16 here, don't get confused. Look, x to the 3rd. Sorry, I cut that off a little bit. X to the 3rd. So this is a 3rd degree polynomial. All right, it's a 3rd degree polynomial, so that makes it odd. And we have a 1/2, right? So 1/2 is positive. So it's positive coefficient. So that means that on the right-hand side, as x goes to infinity, right, as it goes towards the right, or the infinity, okay, this is going to also go towards infinity. All right? But since now it is odd, the left-hand side is going to do the opposite. The left-hand side is going to do the opposite. All right. And if we skip down to 18 here, all right, we have an odd exponent because it's x to the 5th, and we have a negative coefficient, right? So a negative coefficient means that our right-hand side is going to go down. So it's going to go towards negative infinity. And since we have a negative coefficient, the left-hand side is going to do the opposite. So it's going to go towards positive infinity, or go up in the up direction. All right. Now, for 19 through 22, match each polynomial with its graph. All right. So I'll pick 2 of them, and I'll leave the other 2 for you. Okay. So, apologies. All right. So what this can look like here is that we got to remember n equals degrees, right? And if it's odd or even, that's going to mean something. And the max number of turns is equal to n minus 1. Remember, it can have less than that, but that's the maximum that it can have, right? So if we look at graph C here, all right, graph C here, it has 1, 2, 3 potential turns. So it has 3 turns, so it can have up to 3 terms, up to 3 turns. And you can see that it goes up on both sides. If it goes up on both sides, it means it has the same behavior. Since it has the same behavior, they're both going up. That means we have an even exponent. All right? So immediately, that means I'm looking at 20, 21, or 22. Has an even exponent. All right? And since they're both going up, that means I have to have a positive coefficient. All right, so the only one that fits that is 22, And we also got to make sure that last characteristic fits that graph, right? So we had 3 turns, which means our degree can be 4 or greater. And when you look at it, we have a degree of 4, so that graph matches. All right, that graph matches. All right, now if we look at D here, and I'll change colors just for clarity's sake. If we look at graph D here, all right, we have 1 turn, okay? So we have 1 turn, so our degree can be greater than or equal than 2, okay? Greater than or equal than 2, all right? And our graph is going down in both directions, so that means our leading coefficient has to be negative. And since they're going down on both the left and the right-hand side, it has to be an even exponent. All right, so we're looking for an even exponent here. All right, so that limits it to there. Then we're looking for a negative coefficient. Well, that's still both of them. All right. And then it can have a degree of 2 or greater. So technically, both of these would fit here. All right. So what you would have to do is we would have to do process of elimination by seeing which one of these graphs fits better with the other one. All right. And I'm going to let you know that 20 is actually graph D. All right. 20 is graph D. And you'll find that out when you do the other 2 as to why. All right. So then 22 and 23, 23 and 24, I'll do one of these. I really want to have you try one of these out on your own, okay? But the first thing you have to make sure is do you have everything in standard form? Okay, do you have everything in standard form? All right, and we've got a 4, 3, 2, 1, 0, so we are good there. All right, and then we draw our table. All right, so first off, we put our value that we are evaluating for. So we've got f of -1, so you put -1 there. Then you put each of the exponents. So I have, the coefficients. -3, 2, 6, -1, and 6. So 2, 6, -1, and 6. All right. Okay. So I carry this first value down, -3. -3 times by 1. negative 1 gives me a positive 3. I add those together, that's 5. All right, 5 times negative 1, negative 5. Add those together, that gives me 1. Times by negative 1 is negative 1. Add those together, negative 2. Okay, negative 2 times negative 1 gives me 2. Plus 6 gives me 8. So my final answer for f of negative 1 is a value of 8. All right? And if you wanted to check that in your calculator, you would just plug it in using proper parentheses and being extra careful that we are conscious of the signs that we are using. All right? Plus 6. And when you type that into your calculator, that is still going to give you 8. All right. Now, for the last one here, 25, sketch a possible graph. I want you to be able to do that on your own, so I'm not going to tell you how to do that. Okay, but what I am going to tell you is be careful of the exponent, right? So look at the exponent. Ask yourself, is it odd or even, and what does that mean? Okay, what does the leading coefficient mean? Coefficient, what does that mean? Right? And how many turns am I supposed to have? How many possible turns can I have, right? N minus 1. Okay? So figuring out all that stuff. And then you can look at the answer key later to figure out what a possible shape of that graph might look like there. Okay? What a possible shape of that graph might look like. All right? Again, work through those problems. You do have one quiz for this unit, so please make sure that you get that done as soon as possible.